Thank you. Let me thank INSAIT for this opportunity to speak to you, and let me thank you for coming out on a Friday evening. I hope this will be worth your while, not too technical.
There will not be. No, yes, this mic. No,
this mic is only for recording.
Yeah. So one mic.
One mic, okay. Everyone can hear, yes? Good in the back? Okay. And I hope there will be time for questions, but I do have quite a few slides, so let's get started here. Self-adjusting data structures. Let me start by making a few observations. I've been doing this for a long time. I got my PhD in 1972, so that's 2 or 3 or 4 generations of professionals. Since that time, I was in almost at the beginning, so over the last 60 years, computer scientists have developed lots of beautiful and theoretically efficient algorithms and data structures. But this is not, even though what I do really is mathematics, this kind of mathematics has not been done for that long, certainly less than 100 years, most of it. So the field is still young, and often we pick the low-hanging fruit. We settle for the best, the good enough solution. But maybe it's not the best solution. The design space is rich, and computers only get faster. The speed is more, memory size is more. This expands the design space. So my goal in my research is to try to design simple algorithms that people will actually use, but still are the best possible algorithms. Identify the simplest possible efficient methods to solve basic problems, important problems. Paul Erdős, who was a combinatorial mathematician, he was more than a combinatorial mathematician. He had many phrases associated with his name. He had this concept of proofs from the book. This is the book in the sky. So let's think about designing algorithms from the book, algorithms that are as simple as possible, but with provable resource bounds for important classes of inputs, and that are efficient in practice. This was attributed to Einstein, another person who said many things that he didn't actually say, but people think he did. Make everything as simple as possible, but not simpler. So let's go to the subject at hand. What is a data structure? It's a way to store information so that we can get information out of the data structure, and we can also change it. We want to think about dynamic data structures. What is important about these is that we need to know exactly what the operations are that we want to do on the data that will give us information about how to design, how to structure the data. And importantly, the operations are going to be simple, but there may be many of them. And if there are many operations, it's not so important how much it costs to do a single operation. What is more important is the cost of a long sequence of operations. The classical approach to this kind of situation is to design a data structure where every single operation is efficient. But that restricts the possible solutions. It may be a better idea to relax the requirement and just allow the entire sequence of operations to be efficient, allow individual operations to be expensive if there are enough inexpensive operations to balance out the expensive ones. So we want to think about this idea in the design and in the analysis of data structures. Amortize, where does the word come from? It comes from medieval Latin, meaning to reduce to the point of death. To liquidate a debt by installment payments, you take out a huge mortgage and you pay it down in equal monthly installments. So that is the idea. In the analysis of algorithms, we want to pay for the expensive operations by charging them against the cheap ones somehow. And we hope that we're able to do that. And this sometimes, as we'll see in a couple of examples, allows us to go beyond classical worst-case situation, because if we're fortunate, we can design data structures that adapt based upon the way they're used. We can allow data structures that are periodically out of balance or out of best possible configuration, as long as they're in balance often enough. So these are kind of high-level ideas. Let me try to go through two examples now from my own work. The first one will be the Splay tree, which is a self-adjusting kind of binary search tree that was invented by Danny Slater and me in around 1983. Danny was one of my PhD students when I was at Stanford, and he joined me at Bell Labs where I was at that point, and we worked on this together. And then I'll talk about another kind of self-adjusting data structure for that heap or priority queue problem called the pairing heap. This was invented by Mike Fredman and several other people and me in 1986. And in spite of the fact that these data structures have existed now for almost 40 years, we're still discovering new things about these data structures. It's still, we don't understand everything. There is much more to be done, and I hope to make that point here. So let's start with binary search trees. What are they good for? They solve a basic problem in computer science, which is how do you store information so you can get very simple kind of access. So we want to store a set of items, each with an associated key and possibly with some data. And we want to be able to look up items based upon the key. And we want to be able to update the dictionary by adding new items and deleting old items. So we think of a dynamic dictionary. So access operations, those are the queries, insertions, and deletions. We could, of course, use a hash table, which would give us constant time to solve this problem. But then the important thing here is I want to look at data structures where we use the ability to sort on the keys. This takes us to the idea of binary search. I'm going to represent a dictionary as a binary search tree, which is just a concrete representation of the binary search process. So once upon a time when there were actual paper phone books, if you wanted to look up some name in the phone book, you might open halfway. Maybe you're at the M's if you're in Roman alphabet. If you're looking for a name that begins with K, you look in the first half. If it begins with T, you look in the second half. And then you recursively have, and after a logarithmic number of steps, you can guarantee to find the name. So a binary search tree just is a data structure that makes binary search concrete. We store each of our items. In this case, I'm going to not distinguish between the items and the keys. The items and the keys here are just the letters. In the nodes of a binary tree, each node has two children, a left child and a right child, either or both of which can be missing. And the critical property is that the items in the tree are arranged in what is called symmetric order, which means that for any node, everything in the left subtree is smaller and everything in the right subtree is bigger. So for example, F is in the root. Everything in its left subtree, B, D, and E, is smaller, earlier in alphabetical order, and M, P, and X are larger, they're in the right subtree. And this property holds for every node in the tree. So D has two children, B, which is smaller, and E, which is larger, the left and the right child. So this is our data structure. We represent in the computer by storing each of our items in a location, and we need two extra fields at a minimum, a left pointer and a right pointer, so we can implement binary search. So this just summarizes what I've said. The important thing is that if we want to search for an item here, for example, P, we start at F, compare P to F. P is bigger, we branch right. We compare to M, P is bigger, we branch right. Compared to X, P is smaller, we branch left. We've gone through 4 nodes to get to P, and the time taken is constant per node, so the time required is proportional to the length of the path from the item, from the root to the item that we're searching for. So to make accesses fast, we need to make paths in the tree short. The best case, if we're trying to minimize the worst case time per access, would be to put the nodes in layer by layer, balanced as evenly as possible, and when we get a complete or a full binary tree, something like this, where the leaves, the nodes at the bottom, the ones that have only only 0 children, no children, are at the bottom 2 levels of the tree. With this kind of structure, we guarantee base 2 logarithm access time, number of nodes on the access path. If we're given the items in advance, we can construct this kind of data structure, but the problem is when we start doing insertions and deletions, it's not so clear what to do. So statically, this is good. Dynamically, not so good. Furthermore, this doesn't distinguish between which items might be easy to access and which items may be harder to access. The average access time here is logarithmic, and the worst case access time is logarithmic. And there are very few nodes at the top of the tree, so you only get constant access time to some small number of nodes. All right, so how do we do insertions and deletions? First, we'll come up with some way to do insertions and deletions, which is going to ruin the tree balance, and then we'll modify the methods by adjusting the tree somehow to keep the tree balanced enough so we get good performance. Now, the obvious way to do insertion is called leaf insertion. We just follow the access path looking for the node, and we're going to fall off the bottom of the tree somewhere because the node is not in the tree, the item is not in the tree, and we'll just put the new item in a new node where we fell off the bottom of the tree. So for example, in this case, if we wanted to insert R into this initial tree, R is in red, we follow the search path, which goes from F right to M, right to X, left to P, right to R. We fall off from P, we put a new node in that contains R, and then we're done. This is good, but if we take, say, an empty tree and we start inserting items, there's a natural order in which if we do the insertions in this way, we don't get a balanced tree. In fact, we get the worst case tree. If we insert items in sorted order, we put A at the root, next goes B, it's the right child of A, next goes C, it's the right child of B, and so on. The worst case access time is now linear in the number of nodes in the tree, which I'm denoting by N. This is no better than a singly linked list. And the average access time in this tree is N over 2 if you're worrying about constant factors. That's not so good either. So we need to do some kind of rearrangement on insertions to keep the tree much better balanced. Now the classic solution guarantees logarithmic worst case access time by maintaining some kind of balance condition, some kind of local condition so that all path lengths are logarithmic, so all search times are logarithmic. And the rebalancing is some kind of restructuring along the search path so the insertion time is also logarithmic. The original version of this kind of data structure is the AVL tree. AVL stands for Adelson, Velsky, and Landis, who invented this in about 1971. There's a 4-page paper that describes the data structure and how to do insertion. Since that time, many other kinds of balanced search trees have been invented, notably red-black trees and their variants. They were actually invented in 1972 by Bayer, but Gibas and Sedgwick popularized them in a paper where they called them red-black trees. And there are many, many others. So what we need to get this idea to work is some kind of local balance condition and a way to restructure the tree when we do updates to restore the balance. Whoops, that's not good. Let's try this. Here's an AVL tree. So in an AVL tree, the balance condition is that if you start out from any node and you look at the maximum path length, if you go to the left, it's within 1 of going to the right. So it's either the same maximum path length going in both directions, or the right side is longer, or the left side is longer, but only by 1. So if you store a 3-state We could call that a trit, trinary bit in each node. That maintains the balance information. Now, when we do an insertion into this kind of tree, if we insert down a long path, we can violate the balance condition, and the solution is to modify going back up the access path, rearranging the tree locally. So to do that, here's a red-black tree. So in red-black trees, in AVL trees, the flexibility that we need to do insertions and also deletions is this height difference is allowed to be 1 rather than 0, basically. In red-black trees, there's a black basic structure such that any path from top to bottom contains exactly the same number of black nodes, but there are also red nodes. The requirement of red nodes is that a red node is isolated. It has black children and a black parent. So along any path, the shortest possible path from top to bottom would be equal to the number of black nodes, which is the same on any path. The longest a path is twice that, because the nodes could alternate black, red, black, red, black, red. So another name for this kind of tree is a half-balanced tree. Different definitions of balance, but these kinds of trees work essentially the same way. The restructuring primitive, the local transformation, is the rotation, which allows us to take two consecutive nodes, a node and its child, and move the child up and the parent down and preserve the left to right order, the symmetric order. So here we have X is the left child of Y on the left-hand side. We move X up to replace Y, and we push Y down to become the right child of X. And the three subtrees attached, X's left and right children, subtrees, and Y's right subtree, are attached in the correct left to right order to preserve the search ability. 3 pointer changes suffice to do this. The A subtree and the X node move up. The Y node and the C subtree move down. The B subtree stays at the same level, except the parent of the root of the B subtree changes from X to Y. A rotation, this operation, if we do enough of them, this is sufficient to turn any n-node tree on a given set of items into any other n-node tree on the same set of items with the same order. And we can use it to do insertions and also to do deletions. So in AVL trees, in the original description, we do the insertion. If the path gets too long, if we violate the balance condition, we do rotations and recomputation of the three-state information to fix the rebalancing. And the rebalancing proceeds back up the access path. Red-black trees, the same thing. Certain kinds of trees, notably red-black trees, but not AVL trees, you can do the rebalancing preemptively top-down rather than bottom-up. And insertion we do in the same way, roughly speaking. All of these data structures guarantee logarithmic worst-case access time and logarithmic insertion and deletion time. So if all we're interested in is the worst case, a worst-case guarantee, any of these data structures will suffice, and the differences are in the complication of the implementations and maybe in the constant factors. Now, what are the issues with this solution? Well, first of all, the rebalancing algorithms have many cases, especially for deletion, typically 6, including symmetries for insertion, 8 for deletion. And if you have to do the coding yourself and you make a mistake, bad things can happen. You have to store some kind of balance information, but maybe it's tiny, like 1 bit for red-black trees and a 3-state, maybe 2 bits in an AVL tree. But here's a more interesting issue. In practice with these data structures, access is not uniform. We do not want logarithmic access to all possible items in the tree, there may be some items that are much more frequently accessed than others, and we'd like to somehow take advantage of non-uniform access. There could be non-uniform access in space. For example, we're accessing all the small items and all the big items and nothing in the middle, or some kind of locality of access in time. We have some kind of working tiny set of items that we're accessing a lot, and then the context changes to another set of items, so we want to move those up in the tree and have those be accessed fast. The question is, can we get something like this to happen automatically? Now, it's impossible to do with any of these classic solutions, but if we have this idea of amortization, we can try something that's not only simpler, but also might give us good behavior in these non-uniform situations that do in fact occur in practice. So this takes us to the idea of a self-adjusting or self-organizing binary search tree. So the idea is going to be every time we access an item, we're going to move it up in anticipation that it's going to be accessed again relatively soon, so it should be higher up in the tree. And we'll take the extreme position that we're going to move every time an item is accessed, we're going to move it all the way to the root. That has some advantages, as it turns out. And we'll do this via rotations along the access path. So the number of rotations will be proportional to the search time, but once we've moved our item up to the top of the tree, if we access it again immediately, it takes constant time rather than logarithmic time, or however long the access path was. Now the first attempt is just every time you access an item, do the rotations bottom up along the access path. What happens then? Well, we get bad behavior. So here's an example. This is a linear list in reverse order. The largest thing is at the root. If we access the first item, number 1 here, we rotate it to the top of the path, we get the second picture here. 1 moves to the root, everything else gets pushed down by 1. We haven't really improved the tree structure. If we now access item 2, the next one in increasing order, it moves up this path, 1 gets pushed down, 2 goes to the root. This path gets 1 shorter, but it's not getting shorter very fast. If we then access 3, it takes us 1 less to access 3, and you can see the pattern here. After we've accessed 1 through 6 in sequential order, in increasing order, we get back to the original tree. The best case here, well, the access time is what? It's n plus n minus 1, and it's gradually getting smaller, but the total time for all the accesses is n squared. For n accesses, we got to do roughly n squared over 2 node visits, n over 2 per visit. That's linear. We got back to the original tree. This is bad. We want to avoid this situation. So maybe we give up, but maybe we don't. So here's the next try. This gives us the splay tree data structure. So splay as a verb means to spread out. What we're going to do is we're going to do the rotations not one at a time, but in pairs, roughly bottom up. But sometimes we're going to do the top rotation before we do the bottom rotation. Here's the pseudocode. The picture is on the next slide. The picture is probably better. The idea is the following. We started our node that we've accessed. We're going to move it to the root eventually. We look at the next 2 edges going up along the access path. If the 2 edges are in alternating directions, left, right, or right, left, we'll do the bottom rotation first and then the top rotation. That's the zigzag case. If the 2 edges are in the same direction, left, left, or right, right, we'll do the top rotation first and then the bottom rotation. That's the zigzag case. And then if we get to within 1 step of the root, we'll rotate the last edge, and then the node that we wanted to move to the root has made it all the way to the top. So here are the cases in pictures. If we're one step from the root, X is the node being accessed, we rotate it and make it into the root. If we're at least 2 steps away from the root, and the next 2 steps up the tree are a right and a left, or symmetrically a left and a right, we do the bottom rotation first and then the top rotation. We get the middle picture on the right. The zig-zag case is the interesting one, the one where we differ from the purely bottom-up process. We do the top rotation first and then the bottom rotation. This simple change from the pure bottom-up strategy has some interesting, deep ramifications. This is an artist's conception of a self-adjusting search tree. This was drawn by George Stolfi when I got the Turing Award, and it's an illustration in my Turing lecture from 1986. Let me just give you a few examples here. I'm not going to go into the analysis, which is interesting, but we've got a simple data structure here. If we start out with a pure zigzag situation, we access 4, we move it up by zigzag steps. What happens is that the access path gets split in 2. Everything less than 4 is in one path, and everything bigger than 4 is in the other path. And if there were additional subtrees hanging off, they would just be attached in the correct positions to maintain the symmetric order. Even though this zigzag step doesn't necessarily look like it's doing anything good locally, globally it has this nice behavior. It's roughly halving the access path, and nothing gets pushed down by more than an additive constant amount. And here's the pure zig-zag case. If you do one step, nothing interesting happens. But if you repeat it, the nodes along the access path get paired up. So they get split in 2, their parents and children, and the access path again gets roughly halved. So all the nodes on the access path move up by roughly a factor of 2, and nothing gets pushed down by more than an additive constant. And now with an appropriate analysis, which is not so easy to discover, well, before I mention the analysis, let's look at operations on this data structure. The fact that I'm doing move to root is very nice. When I do an access, I will access the item, move it to the root via splaying. When I insert an item, I will follow the access path, insert it as a new leaf, splay it so it's now at the root. And to do a deletion, I'll follow the access path to the node that I want to delete, and then I have to swap it in general with some node on the bottom of the tree. So if I have 2 children, I'll branch either left or right and then go down to the successor or the predecessor of the node, do a swap, delete the node, and then splay along the path. So I move the parent of the deleted node all the way to the root. That's the way I do deletion. In each case, the time for an operation is proportional to the number of nodes on the one path that was traversed, because the number of rotations is equal to the number of edges on the access path. Now, in the worst case, this algorithm is terrible. But in the amortized case, it behaves astonishingly well. And here's something we can do with a move to root heuristic, such as splaying, that's not so easy to do in classical balanced search trees. If I want to put 2 sets together, I've got my dictionary with people from A to M, and then I've got my set from A to Z, and I've got each one in the dictionary in a search tree, and I want to put them together. That's catenation. I splay at, say, the biggest node in the small tree, let's call that X. It moves to the root, and then I merely attach the root of the big tree as the right child of the new root X, and I've put the trees together. Conversely, if I want to split a tree into 2 at a given place, I splay at the node at which I want the split to take place. I move it to the root, and then I can break the tree into the splitting node and everything that's smaller and the set of bigger nodes. We get flexibility here because we have this move to root heuristic. Now here's the bottom line. This data structure wouldn't be interesting except for this fact. Even though individual operations can be expensive, long sequences of operations are fast. If we do M operations on trees that have something like n nodes in them, the amortized time is log n. That is, the total time for the entire sequence is log n times the number of operations. Now, more precisely, it's the sum of the logarithms of the sizes of the trees at the time the operation is performed, because if we're doing insertions and deletions, the sizes change over time. So this data structure, even though it doesn't maintain any balance information whatsoever and can get arbitrarily unbalanced, behaves just as well as standard balanced search trees in this amortized sense. Furthermore, one can prove that for some of these biased access sequences, like you access a bunch of items, small set of items for a while, frequently shift to another set of items. This data structure performs as well as the best possible search tree, knowing this information in advance. Another example is if you have fixed access probabilities, there's a way to build the best possible static tree that minimizes the average access cost. But this data structure does it automatically without knowing the access frequencies. It adjusts to match the behavior. So we were able to prove a number of these special case kind of properties, and we made an audacious conjecture, which is the dynamic optimality conjecture, which says essentially that for any access, so here's the scenario. I give you an initial tree with n nodes. Let's forget about insertions and deletions. I just want to do a sequence of accesses on this initial tree. You know the access sequence in advance, the entire access sequence in advance. Your cost is you need to traverse the path to access each item, and anytime you want, you can do a rotation, and the total cost is the sum of the path lengths for the accesses plus the number of rotations. I do the same operations, and I use the Splay algorithm to do the updates without knowing the access sequence. The conjecture states that the Splay algorithm comes within a constant factor, and it looks like a small constant factor, of the best algorithm for the given access sequence. Now, if this is true, and you don't care about constant factors, and you're happy with amortized behavior, we've got a universally good version of a binary search tree. This conjecture is still open after 40 years. Now here's an interesting recent result related to this. Why do we think the conjecture is true? Well, because of the following fact, which was proved by my PhD student, Caleb Levy, in 2019. What kind of properties does an optimum algorithm have? Well, one is it's going to be monotone. What does that mean? So I have my access sequence, I have my initial tree. Let's suppose I remove some of the accesses. So I made the problem simpler. The total time to do the accesses should become less. And this is certainly true for the optimum algorithm. This is not, in fact, true for splaying. You can construct examples where you drop out some of the accesses, and the Splay algorithm, the cost increases, but only by a constant factor, apparently. If you can prove that splaying is monotone to within a constant factor, then dynamic optimality holds. Furthermore, this is an if and only if condition. So now, rather than thinking about comparing Splay with an arbitrary optimum algorithm whose structure we don't understand, all you have to do to prove or disprove dynamic optimality for splaying is figure out whether it's monotone to within a constant factor or not. Whether this simplifies the problem, of course, nobody knows because nobody has a proof of this, but this is my favorite open problem in data structures. So there's the new goal for all of you eager young researchers. All right, in the small amount of time remaining, let me switch to another kind of self-adjusting data structure. This is a special case of the dictionary problem. Again, we've got a set of items. Each one has a numeric key. And now I want to think of these as really being numbers, because I'll get to an application in a moment. And what we're interested in is storing the set of numbers, but the access is highly biased. Specifically, we only care about getting access to the minimum key, the minimum number. So this would be a min heap, or you could think of the maximum number, that would be a max heap. So we got two operations: insert a new number or a new item with its number into the data structure, and delete the minimum. These are the two simplest or fundamental operations on heaps. We could think of some additional items. So we can't delete arbitrary items. We can't access arbitrary items. All we can do is find the minimum. Now this is enough, for example, to sort, because if I want to sort n numbers, I just insert them into the heap, and then I repeatedly do delete min, and I get the numbers out in sorted order. So we know one of the classic results is that to sort n numbers using binary comparisons takes n log n comparisons. So one of these operations is going to take logarithmic time. So our goal here is somehow logarithmic time for some operation and constant time for all the others. But before we get there, let's look at some additional useful operations on heaps. So here's a fuller set of operations. Make heap just returns an empty heap. We know about insert, we know about delete min. Turns out it's useful to be able to change the key of an item in the heap, specifically by making it smaller. That's the decrease key operation. So I have an item in my heap with some key. I want to grab the item, make its key smaller, so it has more chance maybe of being the minimum. Now, this data structure is non-symmetric with respect to min and max, so decrease key turns out to be an easy operation. Increase key in a min heap is a harder operation. We could do a decrease key by deleting the item and reinserting it, provided that we had an arbitrary delete operation. But that turns out not to be the best way to do it. Now, another useful operation on heaps is to be able to put two of them together. Take two item disjoint heaps and combine them into one. So here's an even fuller set of operations. I'll call these meldable heaps. Meld is the operation of taking two heaps that have different sets of items, combining them into a single heap. Now, if we did this with binary search trees, we don't know anything about the relative order. We would have to basically take one tree apart and insert its items into the fresh tree by sequential insertions. Binary search trees are too ordered to make these operations efficient. We might also want to allow arbitrary deletion. Now, one critical thing here is that I'm assuming that for the operations that need access to an item that's already in the heap, I'm provided with a pointer to the position of the item, the location of the item in the heap. Okay, now what can we do with these? I think I've said this. Our target is log n per operation for certain operations, and we like everything else to be constant time. So many applications, heaps or priority queues, are used in kind of obvious settings where you're doing priority-based scheduling and allocation. That's where the name priority queue comes from. Discrete event simulation, where the items in the heap are events that are going to take place in the future. The key is the time at which the event is going to take place. For example, you're simulating billiard balls bouncing around on a billiard table. Events are collisions with the wall or with another ball. You can predict when this is going to happen in the future. When that happens, trajectories change. So you store the set of future events that you know about in a heap, pull the next event out of the heap, recompute trajectories, recompute the next set of possible events, put those in the heap, and so on. Many network optimization algorithms use heaps, notably Dijkstra's shortest path algorithm, minimum spanning tree algorithms, maximum weight matching, and many others. I've highlighted shortest path algorithms. So what is Dijkstra's algorithm? It's the greedy algorithm for finding shortest paths. For the single source problem, we want to start from some source, find a minimum length path to every possible destination. We have a directed graph. The arcs have lengths, non-negative lengths. Dijkstra's algorithm is a greedy strategy that maintains a priority queue. Each time it removes a node from the priority queue, the heap, it's guaranteed that the key value of that node is its actual distance, shortest distance from the root. Now, if you implement Dijkstra's algorithm in a nice way, it turns out that most of the operations are decreased key operations. Every time you determine the distance of a given node, you need to look at all of its outgoing edges. And if the edge goes to a vertex that you haven't seen before, that gives you a new path to that node, and you know the value because it's the distance to the start vertex plus the length of the edge. But if the edge goes to a vertex that you already have a distance for, you need to compare the path that goes through this vertex with the path that you already have. And if the new path is smaller, you do a decreased key operation on this other vertex that's still in the heap. So we need to do n inserts into the heap, one per vertex, n delete mins to find the distances, and m decrease keys, where m is the number of edges. This is the worst case. N is the number of vertices, m is the number of arcs. In general, in graphs, we have many more arcs than vertices. Classical implementations of heaps take log n time for every single operation. If we could reduce the time per decreased key to constant rather than logarithmic, we would reduce the time bound for the total process for running Dijkstra's algorithm from number of arcs times log n to number of arcs plus number of vertices times log n. And if m is reasonably large, this would become a linear time algorithm. So for sufficiently dense graphs, we would get a linear time algorithm. So this observation led Mike Fredman and me to try to do this, to design a data structure where only the deletion type operations take logarithmic time, and the other operations, notably meld and decrease key and insert, take constant time. And then we would achieve our goal of reducing the worst case time for Dijkstra's algorithm. And here we only care about the total time of all the operations, so we can use this idea of amortization. We could implement a heap as a binary search tree, but it's too ordered. Things are totally ordered. All the operations take logarithmic time. Meld is more like linear time. We need a more flexible structure. So how do we implement a heap? Here's an alternative. Instead of using a symmetrically ordered tree, a tree is a two-dimensional structure. And so there's a left to right order of the nodes, but there's also a top to bottom order of the nodes. Now, the left to right order we think of as a total order, symmetric order. The top to bottom order is only a partial order. All that we require is that, this is going to be a min heap, so we'll require that for each node, its key is smaller, or at least no larger than the value of those of each of its children. So the minimum value is going to be at the root. That's heap order. So our data structure is going to be a heap ordered tree containing the nodes, and the heap order is respect to the keys. So the root is the minimum. We can get access to the root in constant time. Access is going to be through the root, so find min takes constant time. Just as in the binary search tree case, now the question is, what should the tree structure be and how do we implement the heap operations? And it's reasonably straightforward to do this, but the natural way to do it turns out to be not to use binary trees, but to use trees where the degree of a node can grow. So the natural way to combine two heap-ordered trees is to compare their roots, the keys of their roots, and make the root with bigger key a child of the root of smaller key. That combines two heap-ordered trees into one. With the right kind of representation, that's a constant time operation. We'd call that a link. The winner is the root of smaller key, and the loser is the node of bigger key, which becomes a child of the remaining root. We'll build all our operations out of this link, just as we did restructuring in binary search trees using rotations. We're going to use links and the inverse, which is a cut. Just break a link, which breaks a tree into two trees, always maintaining heap order. Here's a link. We have a tree A with key root 10, tree B with root key 8. 8 is smaller, so 10 is the loser, 8 is the winner. The 8 node acquired a new child. So if we're going to use this strategy, the number of children of nodes is going to grow over time, and the trick now is to keep the degrees as small as possible, at least in some average or amortized sense. So here's a heap-ordered tree. The children of a node are the nodes that lost a link to the parent. The first question is, how do we represent this in a computer? Because node 5 here has 4 children. It could accumulate a non-constant number. We can't explicitly maintain a pointer to every single child, so we need to transform the representation. We use a binary tree representation that looks like this. For every node, we store a pointer to one child. Let's call it the first or leftmost child. And then we link the children of a node together, singly linking, or maybe we need double linking. So here, the first child of 5 is 7, which was the most recently linked node, then 16, then 27, then 10. These lists of children are not in any particular order because they lost to 5 at different times. The order of the children is by link time, not by key order. Every time we do a link, the loser becomes the new first child of the winner. That makes linking a constant time operation with this representation. All right, so to find the min, we return the item in the root. To make a heap, we create an empty tree. To do an insert, we take our node, we make it into a single node tree and just link it with the root of the current tree. To do a meld, that's just a link. So far, everything is constant time. To do decrease key, if we're at a root, we can just change the value, which preserves heap order because it's decreased. If we're not at a root, we break the link to the parent. That's a cut. Breaks the tree in two, change the key value, and do a link. So one cut, one link, decrease key. So far, everything is constant time, in the worst case. Delete min, all the work goes into the delete min. So how does this work? We have a root, we delete it. Now we've got this list of children, maybe lots of children. We need to link, each child is the root of some subtree, which is a heap all by itself. We need to link these together somehow to create one single tree. All the flexibility in this kind of implementation is in the delete min, the way we do the linking in delete min. So here's an example. We delete 5, we got 4 children that we have to link together somehow. One can employ here some kind of balance notion, analogous to what we did in binary search trees, This is what Mike Fredman and I did. We invented something called the Fibonacci heap, which keeps some balance information that turns out to be the node degrees, and we only allow linking of nodes that have the same number of children. And that gives us these good bounds and led us to an optimum worst case implementation of Dijkstra's algorithm, and also to a faster minimum spanning tree algorithm, and to many other interesting ideas. Now, there is amortization in the analysis. We don't get good worst case behavior, but there is in here this idea of balancing, and now we want to try to turn to something that's truly self-adjusting, that's not trying to minimize the worst case, but it's trying to minimize the situation no matter what the sequence of operations is. So we're not going to store ranks. We're going to do the links based upon position and the root list. And how does that work? That led to this idea of the pairing heap, which was invented by Mike Fredman, Bob Cedric, Danny Slater, and me in 1986. We do two passes of linking. There's a pairing pass where we link the roots in adjacent pairs left to right, and then an assembly pass where we start at the right-hand end and just link the remaining last root to its sibling until there's only one root left. So here's the picture. I delete 5. I omitted the subtrees, but in general there would be subtrees off these nodes. We'll link 7 and 24, 21 and 18, 16 and 27, 28 and 10 in the pairing pass. Produces this. And then we start from the right-hand end, 10, link 10 to 16, 10 wins, link 10 to 18, 10 wins, link 10 to 7, 7 wins, and here's the final structure. All right. Of course, there are many options here. A multi-pass version of this data structure, we just repeatedly do pairing passes until there's only one root left. Skip the assembly pass. And here's the example of that. We link 7 and 24, 21 and 18, 16 and 27, 28 and 10. That's the first pass. We link 7 and 18, 16 and 10. That's the second pass. Link 7 and 10. That's the third pass. And there are other variants here. Now, why is pairing a good idea? Well, the original analysis of Splay Trees, which I didn't have time to talk about, when we apply it to the original version of pairing heaps, gives us a bound of logarithmic amortized time per heap operation. So we got a pretty good data structure here. And this pairing plus assembly process turns out to mimic the repeated zig-zig on Splay Trees. So it's a little bit of a special case of what happened in Splay Trees, which is one reason we designed this data structure this way. But this really doesn't get at the answer. We didn't know whether this bound is tight for the non-delete operations like insertion, and in particular decrease key. If decrease key is constant time amortized, then we would get a Dijkstra implementation that's quite a bit simpler than Fibonacci heaps. Now, unfortunately, things are not so nice. Mike Fredman proved that with this kind of self-adjusting data structure, you need at least log time per decrease key operation. And Iacono and Ozcan much later proved a similar lower bound, but with different restrictions. So the goal here is to prove or disprove a log amortized time for decrease key in some kind of self-adjusting heap structure. The results for pairing heaps are kind of interesting. Insertion and meld are indeed constant amortized time. Petty in 2005 proved this very bizarre 2 to the square root of log n time for decrease key in pairing heaps. This is less than log n, but it's bigger than log n, and we don't know what the answer is. So another interesting unanswered questions. These data structures that are very simple, it's kind of like function application, you take a simple function and you repeat it over and over again, you can get beautiful fractal curves and things like that. These are data structures where you're doing something very simple, but when you start repeating it, you get complicated behavior that's hard to analyze. Now, I'm way over time here. I will just mention that we have some new bounds, at least for pairing heaps and for related kinds of data structures. You can improve the constant in Petty's result, but more interesting is for multipass pairing heaps, we proved a bound for decreased key, which is within a triple log factor of Fredman's lower bound. So close, but not quite there yet. Constant time for insert and meld. So if you change the data structure a little bit, you can get close to what the lower bound is. And there's another kind of self-adjusting data structure, the slim heap, for which we can prove a log n bound for decreased key. But I want to keep on the subject of pairing heaps here because there's another interesting question. First, what is it that makes these things fast? It's this notion of keeping things in some kind of time ordering. We're linking adjacent roots on the list of roots, which are roots that have lost the link to the parent consecutively. Now, decreased key operations completely screw up the order, so they become a problem. But this idea of keeping things time ordered has other nice properties. And the pairing idea in this amortized sense minimizes the growth in the number of children of the nodes, which is what dominates the running time of this data structure. Still open exactly what the efficiency is. But let's turn to this question of adaptivity here. There's this notion of a working set bound, which I kind of mentioned in the context of search trees, the idea that you're changing the context over time. Well, you can define a similar notion for pairing heaps, and John Iacono in year 2000 proved that the original version of pairing heaps have this working set bound. Now, we did not know for a long time any application of this, but it turns out that this is exactly the right data structure to allow one to devise a very simple and instance optimal algorithm for sorting if you're given pre-existing comparisons. So I mentioned the sorting problem. You're given a set of n items. You want to sort them. You need n log n time if you know nothing ahead of time. But suppose somebody gives you the answer to certain comparisons, like this item is greater than this item, and this item is greater than this item. How do you sort in optimum fashion using the pre-existing comparisons? There's a beautiful algorithm that was emerged out of some work on Dijkstra's algorithm that I did with Bernard Heupler and many of his colleagues at ETH, some of whom are coming here, and we're still actively working on this. There's a beautiful, simple result that relies on this crucial property of pairing heaps. And I'll stop now. Thank you very much for your attention. I'll be happy to answer any questions on any subject if you have questions.
There are no microphones here apparently, so we cannot give you, but you can
rotate halfway up, for example, or you can do the splaying or half splaying only if the access path is long, and you can keep track of how long the path is. There are some interesting variants. The bad thing about splaying is that rotations are expensive, and you're doing rotations every time you do an access. Nevertheless, this data structure is simple enough that it has been used extensively in practice. And in fact, we got the Kanellakis Prize for this work because it's an example of a data structure that's simple enough and solves a problem that people need a solution to. But yes, there are variants of that sort. You have to be careful, but you can do things. Other questions?
Can the Splay tree concept be applied to multi-threaded programs where you need to lock the tree every time? Really slowly.
Again, the root is a hot spot with splay trees. I think this issue of concurrent search trees is very interesting. I don't think splay trees are the right idea, but I think, first of all, some version of splaying where you do things top down rather than bottom up is the right approach. And furthermore, this idea of starting partway down to do the updating works. And in fact, we have one paper on this idea where it's not purely self-adjusting in the sense that it keeps track of number of accesses. So you're trying to bias the tree so that frequently accessed items are toward the top, and you keep some partial information about access frequencies. And we were able to prove some interesting things, and that data structure is designed to be multi-threaded. It's called the count balance tree, the CB tree. Yes.
Have you thought about applying those for like persistent data structures or purely functional programming languages? Because like Splay trees look like they're simple enough, so you can create like dynamic copies of the structure with just like cheap overheads. So
Yes.
like a history.
That's another interesting question. So that's a whole topic in itself, and I could give it more than one lecture on. So the idea is that these standard data structures are ephemeral in the sense that you make a change, the old structure is destroyed. All you have is the new structure. There are many situations in which you'd like to retain the old version or some set of old versions, at least to query, if not to update. So there are the general notion is persistence. We want a persistent data structure so we can go back in the past. This is really useful for version control systems and many applications. And I did some work quite a while ago now on general, first of all, specific solutions to make search trees persistent. Balanced search trees of certain kinds work very well to obtain persistence. And we had some general techniques for making arbitrary linked data structures persistent. And this is clearly tied into the notion of functional programming, because if you can program something functionally, it's automatically persistent. So yes, it's very interesting. Again, splay trees you could make persistent, but just because you're doing lots of changes on each axis, you're going to consume a lot of space. So it's probably not the right solution. You would want to at least modify the data structure to make it make the updates happen less frequently. You can take red-black trees and get a persistent version in which the extra space is constant per update, and you preserve logarithmic access to all versions. Yes?
My shorter question is, how did you come up with the Splay rebalancing transformations? And the longer one would be, is there some theoretical framework that could give birth to such transformations more formally?
The answer to the first question is the first thing we tried failed. The second thing we tried, after we couldn't disprove it, and then finally we came up with a way to analyze it to prove that it works. You try to systematically explore the design space. I think in answer to your second question, there are situations in which the problem somehow should be reducible to some finite combinatorial problem that you can conceivably explore systematically, even by computer, if you could state it in the right way. I've always thought this should be possible on some of these problems. I don't have the patience to actually try to do it, but I think it's a great research topic, actually. In the back.
So for some data
So the question is, I've heard that for Fibonacci heaps use amortization. There is in fact a version that gets the same bounds in the worst case. It's much more complicated, but it does get the bounds in the worst case. And I'm still waiting for that paper to appear in a journal, actually. Can we do something similar with splay trees? Yes, there is a way to have splay trees with a guaranteed logarithmic worst case access time at the same time. That's not my work. If you send me an email, I can send you the citation and track it down. So the answer is kind of hand-wavy yes, at least to the extent of getting the log n bound. I'm pretty sure that you could, the dynamic optimality conjecture, I'm pretty sure is not true if you want a worst case bound. You could construct bad examples probably fairly simply, I'm thinking. So it's a really interesting question. What kinds of data structures, if you get a good amortized bound, you can turn it into a good worst case bound, or where can't you do that? I'll give you another example. So I worked on the disjoint set union problem, the union find problem, where there's a beautiful, simple algorithm that I didn't invent, but I did analyze it. And there, the bound is not log n per operation. It's not log n per operation. It's inverse Ackermann function time per operation, which is something so incredibly slowly growing, you could never detect it experimentally, but theoretically, it's actually there. And this relies crucially on amortization. That is, the bound in the worst case is log n over log n. So there you cannot get an equally efficient worst case result. But this is a good question in general, and it depends upon the data structure. Yes.
From all the data structures, not only the ones you invented or co-invented, but from all that you know, which is your favorite?
I think I just named it. If I had to pick a data structure that I find most intriguing, it's the disjoint set data structure, just because the answer is so bizarre. What is Ackermann function, let alone inverse Ackermann function, doing in analysis of data structures? This is an example of simple data structure, simple operation. You repeat it, you get some kind of deep behavior. Ackermann's function was invented. So Ackermann's function is kind of a diagonalization, or you can think of it as a generalized exponential if you don't know what it is. So plus 2 times 2, 2 to the n, tower of n 2's. That's the sequence of functions. And the next one would be applying the tower of n 2's n times. You diagonalize over this thing, you get Ackermann's function essentially, which grows incredibly rapidly, which was constructed back in the day when people were trying to understand what computation is. We got Turing machines, we got general recursive functions as two equivalent representations of computability. This Ackermann function was constructed to show that you need multivariable recursion in order to get full power of computation. It diagonalizes over all the primitive recursive functions, that is the one variable recursive functions, and grows faster than all of them. So you got this incredibly growing function. The functional inverse is the bound for this very simple data structure. I think it's so amazing. Anyway, good. Yes, and yes.
You mentioned that basically with multi-child keys, with big keys, there are two dimensions, horizontal and vertical one. Those are even more dimensions still?
That is a good question, and I don't necessarily have a good answer for it, except I'll make another observation, which is that there's a way to look at the analysis of binary search trees in a two-dimensional geometric view, where one view is the time of the operation, and the other is the position of the item. And you plot nodes in a two-dimensional grid that correspond to the operations. And then you put extra nodes in that correspond to the rotations, and you have to put enough nodes in to satisfy a certain requirement, and that's equivalent to doing the rotations and measuring the cost. And you can transform this because the two dimensions are kind of symmetric. So if you turn the time into space, then you get something that looks like a heap data structure. And actually these slim heaps came out of this dualization from this, this pictorial way of thinking about binary search trees. So people have also looked at trees within trees, hierarchical kinds of trees, which are used in various kinds of computational geometry settings. So maybe that's the place to look for higher dimensional kinds of structures. Okay, one more.
How often does Splay Tree used in practice? Because in my limited experience in competitive programming, we only use it in linked trees. I'm interested in this, or is it used elsewhere?
I haven't tracked that recently, but they've been used in tables where the access is localized and changing over time. We had a whole bunch of examples, but that was 20 years ago, so I frankly haven't kept track of it. This is an interesting example. The linked cut tree is a data structure built on top of splay trees, which allows you to keep arbitrary trees and cut edges and link two trees together by adding edges and keeping track of values along paths, sums and maxima and things like that. It's a beautiful data structure. We designed it originally to speed up maximum flow algorithms. This is something that has found great use in programming competitions, and as far as I can tell, that's its main use in practice, is solving programming competition problems. So I'm really happy to see it used there, in fact. All right, thank you very much.
Okay, so thank you very much for the nice lecture and for coming to Sofia and Bulgaria on a short notice. So thanks again.